Have you ever watched an AI and just wondered, how did it get so good at what it does? It feels like magic, but it's not. It's not about programming a million different rules. Instead, it's this really incredible story of trial, error, and memory. And today, we're going to demystify one of the coolest methods behind it all, deep Q learning. So, this is the big question, right? You've got an AI, maybe in a video game, or a robot in a lab. It starts with zero knowledge. Absolutely nothing. How on earth does it go from being a total novice to a grandmaster? How does it figure out the right moves when there are literally billions or even trillions of possibilities?
Well, to really get it, you first have to appreciate just how massive this challenge is. We're not talking about writing a simple how-to guide. The worlds these AIs operate in are incredibly complex, constantly changing. Think about a fast-paced video game or even just navigating a busy warehouse.
Think about it like this. For a simple game, something like tic-tac-toe, you could actually sit down and write out a table with the best move for every single board layout. It's possible. But now picture a modern video game. The number of possible situations, what the screen looks like from one pixel to the next, is practically infinite. You couldn't create a rule book for that. It would be like trying to write a dictionary that contains every sentence you could ever possibly say. It's just impossible.
And this is exactly where things get really cool. Instead of that impossible rulebook, researchers came up with a way to give the AI something like intuition, a way to generalize from what it's seen before. And this revolutionary idea is called deep Q learning, or DQL for short.
So what makes DQL so special is that it smashes two powerful ideas together. First, you've got reinforcement learning. That's the super basic idea of learning through rewards and punishments, trial and error. But that alone isn't enough for complex stuff. So DQL pairs it with a deep neural network, which is this incredible tool for finding patterns in messy, complicated data. When you put them together, you essentially give the AI agent a flexible brain that can make smart guesses instead of needing to memorize every single possibility. Okay, but just giving an AI a brain isn't the whole story. You see, an AI that's just learning on the fly can get really confused really fast. It can develop bad habits or just get stuck. So to solve that, DQL uses a couple of incredibly clever tricks, kind of the secret sauce, that make the whole learning process stable and way more effective. Here's the problem they had to solve. If an AI only learns from what just happened, its view of the world gets really shaky. It's like trying to learn to drive by only remembering the last 1 second of the road. You'd be swerving all over the place. It creates this jittery, short-sighted agent that never develops a real, long-term strategy. It needed a bigger picture.
And this brings us to the first brilliant solution, the replay buffer. It's basically a memory bank. Instead of the AI learning from its experiences one by one as they happen, it stores them all away. We're talking thousands of them. Then, when it's time to learn, it just pulls out a random handful of these past memories. This simple trick is huge because it breaks up the flow of time and stops the AI from getting obsessed with its most recent actions. It's learning from a rich history of everything it's ever done, not just what it did a second ago.
The second trick is just as clever. It's called the target network. Imagine trying to shoot at a target that's constantly moving. It's almost impossible, right? The AI faces the same problem. If the goalposts are always shifting while it's trying to learn, it just gets confused. So DQL creates a second, slightly outdated copy of the AI's brain. This copy holds still, acting as a stable target to aim for during training. It's like having a teacher who doesn't change the lesson plan every 5 seconds. It gives the AI a consistent, stable goal to work towards. So, let's put this all together. It creates this awesome self-improving loop. The agent sees the world, it picks an action, it gets a reward or a penalty, and then it stores that whole experience in its memory buffer. Then, it pulls a random batch of old memories, learns from them, and updates its brain. And then, it just repeats that cycle, over and over and over again, thousands and thousands of times. And with every single loop, it gets just a little bit smarter. All right, that's enough theory. To really see the magic of this, let's look at it in action. We're going to use a classic AI challenge, something called cart pull. It sounds really simple, but is actually a perfect way to see this learning process unfold. The setup is exactly what it sounds like. You've got a little cart on a track, and there's a pole balanced right on top of it. The AI's only job is to push the cart left or right to keep that pole from falling over. That's it. For every single moment it keeps the pole balanced, it gets 1 point. The game ends the second that pole tips too far. Now, when it starts, the agent is a complete disaster. I mean, it's just moving randomly, the pole falls over almost instantly every single time. But with each one of those failures, it stores the memory. And slowly, little by little, it starts to connect the dots. Hey, when I did this, the pole stayed up just a little bit longer. And through thousands and thousands of these trials, a real strategy starts to emerge from all that chaos.
So after all that training, all those thousands of attempts of fumbling, failing, and learning, the agent went from a complete amateur to an absolute master of the cart pole. And what was its final score? Get this, a perfect 500.
And listen, 500 isn't just some random high number. That's the perfect score. It is the maximum reward the simulation will even allow in one go. So that means the agent didn't just get good. It figured out a nearly flawless, optimal strategy for balancing that pole, all by itself, from scratch.
So you might be thinking, okay, a computer program can balance a virtual pole. Who cares? Well, it turns out this is a huge deal, because the principles that let it master that simple task are the very same ones that unlocked the entire next generation of AI.
This DQL approach was an absolute game changer. It was one of the very first times an AI could learn to play complex games just by looking at the pixels on the screen, the same way you or I would. This technique became the foundation for everything that came next, from AIs that could beat any human at Atari to the one that defeated the world champion at Go. And today, it's a critical tool for training robots and autonomous cars in the real world.
And that really brings us to the final thought here. That journey from a clumsy pole balancer to a strategic master is just a perfect demonstration of machine learning. It proves that if you combine simple trial and error with a powerful memory and a stable learning process, an AI can build unbelievably complex skills, all on its own. Which leaves us with one massive question. Now that they've mastered these virtual worlds, what real-world challenges are they going to master next?